At least if you are not able to find time for doing all the assignments, at least do those problems which I discussed directly in the class. And at least this compute NCR problem was a problem that I showed you how to do it in the class. At least these problems you should have prioritized and gotten it done. Similarly, today also, once we are done with graph DP, I'll show you probably some problems with graphs as well, how to do them. So please try to get them done, or maybe I'll figure out a way. Maybe we can get them done in the session itself, if possible. We'll see how it goes out, but at least those problems, simple, basic problems, you get them done. Only then you will lose the fear of, tackling problems. At least if you have those problems. If you don't have that, good, then you can directly tackle them done. Anyway, let us move on with our today's discussion, which is a very popular and very interesting problem. Which is nothing but the knapsack problem. The knapsack problem. Let's start off with our knapsack problem here. So I'll explain you the question here first. So the question here is basically, you are given 3 items, item 0, item 1, and item 2. You are given the capacity of your knapsack, which is K. Let's say the capacity is 50. You need to calculate what is the calculate the max value of items that fit in knapsack with a capacity K such that sum of weights of items doesn't exceed K. Calculate the maximum value of items that fit in the knapsack with the capacity K such that the sum of weights of items doesn't exceed K. So here there are different variations of this problem. For a knapsack problem, there are different variations. So the first kind of variations that we have is it a fractional knapsack are we talking about, or is it an integer knapsack that we are talking about? And in integer knapsack, again, we have 2 common variants, which is it an integer 0, 1 knapsack that we are talking about, or is it an integer infinite knapsack that we are talking about? I'll explain you each of these variations one by one, but just make a note of the question first. I'll give you 30 seconds. Last 10 seconds. All right, so here, first we have a fractional knapsack. So first I'll explain you what the input is here, okay? W is the weights of those items that are given. V is the values of those items that are given. So item 0 has a weight 10 and a value 60, weight 20 with a value 100 and so on. So the idea behind fractional knapsack is something like this. So imagine these items are something like, for fractional knapsack, imagine that they are something like, petrol, kerosene, and maybe diesel. So with a fractional knapsack, what you can do is you don't have to take the entire weight of 10, the entire weight of 20 into your knapsack. Even if you take a fraction of the item, it will preserve the same fraction of the value. Like, for example, petrol, kerosene, diesel, it doesn't matter if you're removing 100 ml from 1 liter, that 100 ml will retain its relevant value of that fraction. So compared to integer knapsack where you have to take the item whole, this is a very convenient situation for us where you can take a part of it only when you want. For a fractional knapsack, how would you want to approach it? What do you think that you can do here in such a way that you will optimize the value that you are going to store in your knapsack? Or you tell me what is the answer here. Better do it that way. So if it is a fractional knapsack, what is the maximum value that I can store in this knapsack? Um, 250. Okay. 50 is, you're talking about weight. If you're saying 50, most likely you need to talk about the value that is associated with it. $300, $220, $300, $220, $220. Okay. 300, 300, 220. Fine. Let's see, guys. Let's see. So the answer here is, I don't think it's 200. I don't think it's 220, and I don't think it's 300. See here, why did you say 300? So what you were trying to do here is you were trying to pick this item number 0 again and again and again and again and again until your knapsack is filled with it, because it has the highest value per unit of weight. But in a fractional knapsack, taking it again and again is not an option. A fractional knapsack, either you can take it as a whole or you can take it in any fraction of it. So if I give you 1 liter of diesel, you don't have 5 liters of diesel there. You only have 1 liter of diesel from which you can pick any amount that you want. That is a fractional knapsack. So that's the reason 300 is not an answer for us here. So if I have to write the value per unit weight calculation for all of these, so it will look something like this. So here we get 6, here we get 5, and here we get 4, right? 60 by 10, 100 by 20, and 120 by 30. And here, I already have them in a sorted order, but if it is not in a sorted order, you will have to sort it based on this ratio so that you can, prioritize what you want to pick. Then once you do that, you will pick the first item because it has the highest value per unit weight. So the first item will have 10 weight with a 60 value. And then the second item also can fit. So you'll pick that 20 weight with 100 value. But the third item won't fit entirely. See, your knapsack already has a weight of 30 in it. but your knapsack capacity is just 50. You can't add another 30. It will become 60. It will exceed your knapsack capacity. So that last item that we have, we should take only a fraction of it. Which fraction? We want to take only 20 units of weight out of 30. Means we want to take only 2/3 of it. So 2/3 of it, which is 20 units of weight out of 30, is 2/3 of this value, which is 80, giving us the total answer as 240 as the value that you can get for a fractional knapsack. That's right. You can't take an item more than once in a fractional knapsack. In a fractional knapsack, you can take it entirely or take any fraction of it. So our code will look, or our logic will look something like this. First, you will sort the W and V arrays based on V by W ratio. First, you will sort both the arrays based on their V by W ratio. Then maybe you can create something like a total variable or something for the total weight that you're going to store in there. And then for each I equal to 0 to I less than n, you basically have to check if total is basically, I think it's a bit ambiguous. We should put it as total value and total weight that we are putting in our knapsack. Total V and total W that we are putting in our knapsack. So if the total weight you added to the knapsack, when you subtract it from the K value, which is the capacity of our knapsack, that will tell you how much is remaining capacity of your knapsack, right? K minus what you put will be the remaining capacity of your knapsack. If the remaining capacity of your knapsack is greater than or equal to, not exactly zero, you can directly compare it with the item's weight that you're comparing it with. If your knapsack can still, accommodate this ith item, then we will take it into our knapsack. Total value plus equal to Vi and total weight plus equal to Wi. Otherwise, we will take a fraction of it. And you will take a fraction of only the last item, right? But yeah, there are some edge cases around it, but I'll just show you the general code. Edge cases you can handle when you're writing the actual code for it. Otherwise, you just take the item and its fraction. So that fraction that you have to take, how will you calculate it? What is the fraction of the last item that you have to take? Perfect. Perfect. Exactly. Exactly, guys. K minus total weight, which will tell you the remaining capacity, divided by the weight of the item that you have. That is the fraction that you can take into your knapsack. So you can simply do total V plus equal to V of I into fraction. Similarly, total W plus equal to W of I into fraction. Yes, you could also break here if required. Because the fraction that you're taking is often the last item that you're going to put in your knapsack. So you can take that whatever fraction you're taking and you can break. Or you can return total V. Yes, that is also completely fine. Or you can return the total value that you calculated. That is also fine. If you observe carefully, this is nothing but a greedy approach, right? We are just prioritizing what is the best value that we can get right now. And we are taking that. So this is a greedy approach. So for a fractional knapsack, greedy approach will work directly. You can take a greedy approach directly if it is a fractional knapsack. Last 20 seconds, then we'll move on to next variation of the knapsack. Okay, moving on to the next variation of knapsack. That is right. For fractional knapsack, greedy is the best approach. Now moving on to the next variation, integer 01 knapsack. So first we will discuss what is integer 01 and integer infinite. After that, we'll discuss solutions for it. So for integer 01, the idea is instead of petrol, kerosene, or diesel, imagine these are something like mobile, maybe a laptop, and maybe a, I don't know, monitor. So, something like that. So, mobile, laptop, monitor, you cannot take, a part of mobile and expect it to have same value, right? Exactly. You can't break it into parts. Either you have to take it completely or leave it completely. So these are the only two options. That is why it is integer 01 knapsack. Take it or leave it completely. If you break it, it will not return its value, like how petrol or in our example, like how the other items were returning their value. And in integer 01 knapsack, there is only one occurrence of each mobile, laptop, and monitor that is given to us. Whereas in integer infinite knapsack, there are infinite occurrences of these mobile, laptop, and monitor. So first, integer 01 knapsack, what is the answer? What is the best value that you can put in your knapsack? 220. That's right. 220. That is the only option that we have, right? Take item 1 and item 2. What about integer infinite knapsack? The best answer that we can get is 300. Perfect. Perfect. This is nothing but taking the item 1 again and again and again and again and again. In this example, coincidentally, the highest V by W ratio item is giving us the maximum value. But that may not be true in all the cases. Unlike fractional knapsack, integer 01 and integer infinite, you cannot employ a greedy approach there. So first we'll discuss integer 01 in detail. Integer 01 knapsack first. We'll take a more appropriate example. Something like something like this. Item 0, 1, 2, 3, 4. And let's say the capacity of our knapsack here is 7 in this example. Now let's try to frame it as a DP problem. I mean, we'll first see if it has any DP properties or not. In question, will they mention the type to use? Yes, they should mention. Otherwise, it is very ambiguous question. You can interpret however you want. So the first step in our problem solving journey in DP is to identify DP properties, right? And we know how to start that process. We will imagine that there are a lot of items, right? We are at some exactly ith item. But that is not the only dimension we should consider here. We should also consider J, which represents weight left or the remaining knapsack capacity. J is the knapsack capacity. So now you are at any ith item in this calculation and you want to know what is the best value you can get for J capacity. I'll write here so that you can understand as we discuss ith item and J capacity. Now, can you tell me what are the options that we have at this I, J? What can we do at this ith item? We can. Exactly. We can take it or leave it. That's right. We can choose to take ith item or not. That's right. So we have only two options, take it or leave it. So let's say you are at any f of I, j. Let's say you take it. Can you tell me what is the remaining subproblem? What is the remaining subproblem? It's not I plus 1. It's not this. From the remaining I minus 1 items, what is the best that you can do? Right? You don't look forward into the future. You always rely on your past states. I mean, you can also look forward into the future, but that will complicate your DP logic and everything. It is simpler if you just rely on your past states instead. Perfect, guys. From the remaining I minus 1 items, what is the best value you can get for capacity? J minus weight of that ith item. What is the best value that you can get for the remaining capacity? J minus weight of that item. And can you tell me for leave it? That's right. That's right. I minus 1G. I minus 1G. From the remaining I minus 1 items, you still have a J capacity because you did not take that item. What is the best value you can get for J capacity? Before we dig deeper into this, first let's try to see, how this will fall into place for us here. Let's take, for example, here some item. Let's take 4 and 2. If you take item 4 and item 2, now you have filled 6 capacity of your knapsack. Now the remaining capacity is 1. What is the best value you can get for the remaining capacity? 1. That could also happen if you take only 6, for example, here. If you take 6, now again the remaining capacity is 1. What is the best value that you can get for remaining capacity 1? So what I'm trying to show you here is the overlapping sub-problems part of the problem that we have. So here also we have overlapping sub-problems, means you will need the same state again and again for a future calculations. But not only that, you don't want any value, right? You want the best value. You want to optimize your answer. So it also has, exactly, it also has the both the properties, overlapping sub-problems, and it also has optimal substructure property, optimal substructure. So obviously we can take this ith item into our knapsack only when the remaining capacity is more than the weight of item. Otherwise you can't take it. So let's say the remaining capacity is more than the item. And now you want to write a DP expression for this. Can you tell me what should be the DP expression? What is the DP expression here? It's okay, or if you're wrong, just, throw your answers at me. Let your brain work. You have two options. You want to optimize the value that you can get for DP of I, j. Zoom doesn't allow you to copy. So if you try to copy paste your answer, that's what will happen. Add both, definitely not. Both are different options. You can choose only one of them. You can't both take and not take the item at the same time. Schrodinger's cat. So, no. Okay, great. Everyone is like partly correct, but you are mostly wrong because partly correct is considered wrong. Of course, you will take a max of it. That's right. That part, everyone, was able to get it right. I minus 1, j minus w of I. And I minus 1, j. But the part that you missed is this. Plus v of I, value should be added, right, to your DP ultimately. Where did I write? Plus v of I shouldn't come there. Just a second. Sorry. Let me correct it quickly. Yeah, it should come with the take it option. It should not come outside the max. This is glitching like anything today. Okay, great. Now I got it. Yeah, that should come over here. So maximum of these two options, because when you take it, you're adding that value to the answer. So we are adding V of I to the answer in that first option that we are considering. And the second option is whatever is the best you can get for I minus 1G. In the else part, you will not consider the first option. You will only consider the second option. Sorting is irrelevant in this calculation. So the order of elements doesn't help you identify what is the optimal option that you have. So if you do not understand what we wrote here, and if we move forward, you will not understand anything after that. So if you have any doubts still here, you should ask, like, right now. That's right, Bhargav. I'll show you exactly how it works. I'll help you visualize in detail exactly how it works. Before we move forward, any doubt till here? In max, always the first argument is taken then. That is not true. I will show that to you when we can trace it out for this example that I wrote here. I'll trace out how it works for this example. So you'll understand, where we are taking it, where we are not taking it, etc. I can't understand how just dB of I minus 1 is helping. So the idea here is something like for if you are going to make a decision on ith item, you want to know what is the best you can get for the remaining I minus 1 items. So instead of I, you can imagine it like, N and K, for example. So let's say you want to know what is the best that you can get with N items and K capacity. So you have a decision to make. So if you're making a decision on the nth item, you want to know what is the best you can get from the remaining N minus 1 items, right? So if you're making a decision something on the nth item, you want to know what is the best you can get from the remaining N minus 1 items, right? Okay, I assume there are no more doubts then. So let me help you visualize this a bit more. But before that, obviously, first let's finish out where is the answer step. My point is, can't we take ith item right after? We can't take ith item right after first item. We can take ith item after first item. Yes, of course. You will be able to take it. So we'll skip the other steps, guys. I understand there is a problem here with visualization. You're not able to understand how it is working. So what we'll do is we'll just jump right into the visualization directly. After that, we'll discuss all the other points around it. Okay, let me just copy this example down. And let me create a matrix of size. What should be the matrix size, guys? What should be the matrix size? N plus 1, k plus 1. Yeah, I mean, you can go with n plus 1, k plus 1. In fact, it will probably simplify our base condition further. But we had to go with n comma k because you only had have n items, right? Not n plus 1 items. But okay, we'll go with n plus 1, k plus 1, which will actually simplify our answer. And let me show you how. Okay, this is n plus 1. And this is k plus 1. N is 5, so we go till index 5. K is 7, so we go till index 7. But because we are taking n plus 1, now 0th item is not going to represent 0th item. First item is going to represent 0th item. This 0 array is just for simplifying our base condition. You are not doing anything with it. Row 1 will go till first, is representing your answer till first item. Row 2 is representing your answer till second item. Row 3 is representing your answer till third item, and so on. Means if you're taking, if you're doing this extra row here, then in your DP state, you should be careful with this, okay? When you're taking max of these two things, I minus 1, j minus w of I. Now, for row number 1, 0th item, right? Row number 2, first item. Row number 3, second item. Means you should do weight of minus 1. Ith row. This is ith row, right? If I is 1, 0th item, minus 1. 0th row is dummy for us. Following? Clear? Kind of. N plus v of I minus 1 again. And the other thing will not change. Because one extra row is added here to simplify our base condition, basically, we are offsetting it by 1. Yes. 0th row doesn't represent anything. Or you can say it represents when there are no items, something like that. 0th row is taken only to help us simplify our base condition. So when you are at first row, you will need minus 1 every time, right? So instead of writing if I equal to 1 or if I equal to 0, 0, something like that. Now it will go to this index, take 0, and our answer is calculated. Okay. So I'll show you the first 2 rows. Then you try doing the next. I'll show you the first 2 rows. Then just try. I'll show you the next 3 also. But first you try and then I'll show you. J equal to 0 is all zeros. J equal to 0. Yeah. Basically, J equal to 0 will also be all zeros. That is right. Capacity 0. Nothing can be added to your knapsack. So total value is 0. So I hope you are having the context here that this is the capacity dimension, this is the items dimension. All right, we'll just start tracing it out first. For row number 1, we are only going to write what is the best answer that we can get till the 0th item. So capacity 1, the item weight 3 doesn't fit. So we write 0. Capacity 2 doesn't fit. Capacity 3, it will fit. So we will take that. Whenever it doesn't fit here and here, it is directly taking dp of I minus 1j, right? It will not consider this case. If you look at the code above also that I wrote, if it fits in our capacity, only then we do this. Otherwise, we'll directly take whatever is in the above row. So the 0 is basically coming from here when it doesn't fit. At this index, it will actually fit. So we are taking max of 0 plus 12, 0. At this index, dp of I minus 1 is 0. And j minus w of I minus 1 is basically 3 minus 3, which is also 0. So dp of 0, 0 is 0. To that, you are adding plus v of I, which is 12. When you took the maximum of these two, you got 12. And that's how we got 12 in this index. Similarly, for the next index, you'll get 12. But instead of dp of 0, 0, it will now become 0, 1, which is also 12. Sorry, which is also 0. Again, 0 plus 12, 0. 12 is bigger. Again, filling this, it will come from here. The 0 will come from here. Filling this, the 0 will come from here. Filling this, the 0 will come from here. Let's fill the next row now so that we understand how it plays out for us. I mean, for next row, you can't really understand because 6 plus 3 is 9 and you don't really get to fit both the items in a capacity of 7. But at least we'll see how the max will help us in this calculation here. Okay, for the next row, we want to know what is the best that we can go till the item number 1. Okay, first, when you're at column 1, this doesn't fit, right? Item 1, weight is 6. So whenever it doesn't fit, what will we do? We'll take whatever is in the above row. dp of I minus 1j. Whatever is above, whatever is above, whatever is above, whatever is in the above row, and whatever is in the above row. Because till here, this item will not fit. Because its weight is 6. So now here, this item will fit. Now we will consider the first option also in our dp expression. Now we'll say that, okay, what is the best you can do? What is the best you can do with dp of 1, j6, weight of item is 6, plus 20, or whatever is in the above row, which is 12. dp of 1 cross 0 is 0. Sorry, not here. dp of 1 cross 0 is 0. 1 cross 0 is 0. So this is basically 0 plus 20 versus 12. Obviously, 0 plus 20 is bigger. So we will get 20 over here. And when we are filling the next index, the dp expression will become dp of 1 and 7 minus 6. J minus W of I, right? J is 7 in the last column, which is basically just now 1 comma 1. So again, dp of 1 comma 1 is 0 plus 20 versus 12. 20 is bigger. So we take 20 again. Try filling the remaining. Let me know once you're done. Done. Done, done, done. What is the answer that you got? 21, 22. 22. Okay. So, all right, let's see. Item number 2 for row 3. Doesn't fit, doesn't fit, doesn't fit, doesn't fit. Here it fits. 15 plus 0 versus 12. 15 plus this 0 versus 12. 15 plus this 0, sorry, versus 20, right? This is not versus 12. Versus 20. And 15 plus this 0 versus 20. So 20 is bigger here as well. Okay, moving on to the next row, which is this item. Doesn't fit, so 0, whatever is above. Here it fits, so 6 plus 0 versus 0. Again, 6 plus this 0 versus 12. 6 plus this 0 versus 12. Sorry, 12. And 6 plus this 12 versus 15. So 6 plus 12 versus 15. 6 plus 12 is better. Exactly. Here we get 18. 6 plus 12 versus 20. And lastly, 6 plus 15 versus 20. Here we get 21. Here we get 21. And last item, item 4. 0 over here, 6, 12, doesn't fit in all these situations. Here it fits, so 10 plus 0 versus 12. 10 plus 10 plus this 0 versus 18. Then 10 plus 6 versus 20. And lastly, 10 plus 12 versus 21. 10 plus 12 is bigger. So 22 over here. So now if you observe, to get the answer 22, we took whatever is the best from the previous row at this column here, right? And the current item. So whatever is the best at this column is not actually this item. It is some other item that came from, above, or maybe it is that item. But whatever is the best for that capacity till the previous item, that is 12, that is what we are taking. How you are getting 12, that is a different case. Here, if I backtrack, let's say I want to identify, okay, I want to know which items I took. So to know which items I took, I basically have to know if I went with option 1 or option 2, right? At every cell. As simple as that. Our answer is 22. So obviously we should start from there. We should start from the cell. Exactly. We will start from the cell n, k. That is where our answer is. So dp of I minus 1 j, as we know, is just the above row. So check if it is same as the above row. If it is same, it means that you didn't take that item, right? You went with option 2. N plus 1, k plus 1 is the array size, matrix size. N, k is where we have the answer. So here you're comparing 22 with the item above it, but you see that, okay, it is not matching. Then where did this answer come from, this 22? How will you know? How will you know where this 22 answer came from if it did not come from here? Index, okay. 12 plus 10. You know that because you saw me do it. But just looking at the data, how will you go back? That's right. J minus W of I. Exactly. J minus W of I, or I minus 1 in this case. So basically, this is J, right? You're in this column, capacity 7. W of I minus 1 is 4. Means you got this answer from 7 minus 4th column. That is our first option here, right? dp of I minus 1 and J minus W of I minus 1. So we are going to 7 minus 4th column. You got the answer from here. Means we took this element. We got the answer from here. Okay, let's see where we got this answer from now. This answer is matching with the element above it. It means that we did not take that element, I minus 1j. Again, 12 is matching with the answer above it. It means that we did not take this item also. Again, 12 is matching with the item above it. It means that we did not take this item also. But here, this item is not matching with the cell above it, right? It means that we took this item. Where did we get the answer 0 added from? We got it added from here, right? Again, j minus weight of that item 3 minus 3, 0 in the previous row. Exactly, 0th item in the previous row. 0th item weight, you will subtract it from the current column, j minus W of I. It will tell you where you got that answer from. And once you reach here, you will stop, obviously. Exactly. So row 1 represents 0th item, right? And row 5 represents 4th item. So 0th item and 4th item are there in the knapsack to give us a total weight of 22. Following guys, please make a note of this also. How to backtrack on matrix to find the items that we selected into the answer. Please write down as many details as you can. You will need them when you are trying to implement them. Last 10 seconds. All right, now here. So regarding the other things, now base condition is what we are going to discuss. I think you can already see what's the base condition here, right? If you take an extra row here and fill it with zeros, that is very helpful. And we can also have the first column filled with zeros. So basically dp of I0 and dp of 0j is equal to 0. These are our base conditions. And let me just fill all the other steps. Table size, I think I wrote it already there, n+1, k+1, integer array. Time complexity, space complexity, space optimized table size. What is the space optimized table size, guys? No optimization if you want to also print the elements you have taken. If you only want the maximum value, then that is right. 2 cross k+1. Perfect. 2 cross k+1. You only need one current row and one previous row, right? dp of ij, that is in current row. I minus 1 j or j minus w of I, whatever it is in the previous row. So you only need one current row and one previous row. And that will help us optimize the space to 2 cross k+1. For checking where the answer came from. So if you want to know which elements you have selected, then you cannot have a space optimized solution there. That is right. If you only want to know what is the max value, then you can do space optimization. Okay. Last 10 seconds, then we'll move on to the integer infinite variation. Sure, Lokesh. Here. Moving ahead to integer infinite knapsack variation. Now, for integer infinite knapsack variation, let's say you are at any ith item with a j capacity. What is best value that you can get? What are your options here? At I comma j, what are your options? Don't take or take any number of times. Okay. Take any number of times or leave it. Take until j less than w of I. That might not be the best idea. Zeroth item has high ratio. So here, if you just go based on ratio, again, it will not give you the optimal answer. So for example, let's say I have items A, B, C, D with the weight P, Q, R, S. For example, let's say this is sorted weight by W. Okay. Now, you can't say that 3A plus, or let's say you take 3 and your knapsack capacity is full. You can't say that 3A is bigger than maybe B plus 2C. You cannot say that. It is not guaranteed. Maybe taking it, something like A plus 2B would have been better. Maybe taking it as, 2A plus 3C would have been better. So there can be other options that you should consider. You should not take, to the maximum extent that you can. That will be again a greedy approach. A greedy approach doesn't work in this case. So based on that, I understand your intention when you say, okay, we can leave it or we can take any number of times. But the way that we frame it is going to be slightly different. We are going to go again with take it or leave it. Take the ith item or leave the ith item. If you leave the ith item, obviously the remaining problem is going to be I minus 1j. Fine. But if you take the ith item, the remaining problem is going to be that's right. Perfect. Perfect, guys. The remaining problem is going to be you should still consider ith item, but reduce the capacity by j minus w of I now. So instead of the previous I minus 1 items like we had in 0, 1 knapsack, now it will still previous I items itself. But with the reduced capacity, but now that you take, now that you have taken it, now your capacity will reduce. So from 0, 1 knapsack to integer infinite knapsack, the only difference is going to be just this one variable. In fact, if I go up and if I simply copy paste, then everything will work as it is for integer infinite knapsack, with the small exception that this will not be I minus 1, this will be I, that's it. Everything else is same. Every single thing will be same. Just one small change. In fact, you can, make it look like one character change. I minus 1, if I make it I minus 0, it is one character change from integer 0 1 knapsack to integer infinite knapsack. V of I minus 1 or V of I. That depends on that extra row that you're adding in the matrix. If you're adding that extra row, V minus 1. If you're not adding it, V of I. Last 10 seconds, then we'll move on to our next discussion. That is right. This will also have both the DB robotics, overlapping subproblems, and optimal substructure as well. Okay. Also, fun fact, my final year major project was based on a problem, which is based on knapsack. It was something like quadratic bottleneck knapsack problem, which is a different variation of knapsack problem, but it's very, what do you say, too complicated. And it is an NP complete problem. You know what NP complete is, right? NP hard, NP complete. Kind of. No idea, never heard of it. Okay. NP complete problems are basically where it will take a non-deterministic polynomial time to come up with an answer and to verify an answer. Those are basically NP complete problems. And the quadratic bottleneck knapsack problem that we worked on was an NP complete problem. So we had to do a artificial intelligence based approach to find an approximate solution. We cannot verify if it is the actual solution, but it will be an approximate solution for that problem. And we used a technique called swarm intelligence. In swarm intelligence technique, we used a technique called I forgot. Basically, it is based on bees and how bees behave. I forgot its name. Yeah, it's not exactly for feature selection, more like, we had a data set and we had to run that algorithm to come up with an answer for the given data set. It was a huge failure, which is besides the fact, but that is what we tried to do at least, and we convinced our faculty that it is working. No, it is not a neural network. It is just a swarm intelligence technique. Swarm intelligence is not exactly based on neural network. It is based on something else. Yeah, you should know better. Yeah, I don't really want to talk more about it because I don't know much about it anymore. So we'll move on to our next discussion, which is me understanding if you understood what I tried to help you understand. I'll give you a bunch of questions. You just try to give me the DP expressions for it. No nonsense, nothing. Just give me the DP expression directly. In fact, it is fine if you don't even write it, but maybe I'll give you time at the end to write it. But focus on answering instead. Something like a rapid fire. We'll do it like a rapid fire, okay? And that rapid fire is a rapid fire of DP expressions, basically. So let's say I have an array of size n here. And let's say I have k, which is something, doesn't matter. So the first question that I'm asking you here is, let's say this array represents denominations of the coins that we have available. You need to tell me if it is possible to get a change for k. So in the first variation, you only have one occurrence of each coin. I give you k40, right? Now you should tell me if I can get a change for 40 units using the coins that I have, 8, 10, 5, 13, 20. If it is possible. So your answer should be a Boolean, something like a Boolean, true or false. Tell me what is the DP expression? Imagine there are a lot of coins. You are at ith coin with remaining change to be figured out for j units. What are your options? And what do we do with those options? Please don't focus on writing the question in your notes. I'll give you plenty of time. Focus on answering me right now. Fine, tell me at least what are the options? You're at ith coin. What are the options? Ith coin, j remaining units that you have to find change for. What are your options? It's not exactly max. You want to know if it is possible. Or, that's right. Or, perfect, guys, perfect. Take it or leave it. That's right. You got it. If you take it from the remaining I minus 1 coins, you want the sum for array of I, j minus array of I. If that is possible, you will take that. If it is not possible, then you will try to leave it. I minus 1j. So either take it may give you the answer or leave it may give you the answer. Either one of them, if it gives you the answer, then you found the answer. It is possible. And if it is infinite coins, if it is infinite coins, nothing to do with, and here I instead of I minus 1. Perfect. 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 dp of I j minus r of I, or dp of I minus 1j. Or dp of I minus 1j. So here, only this will change. Nothing else will change. From 0, 1 coins to infinite coins. Okay, next variation. What is the minimum number of coins to get change for k? Minimum number of coins means if you take this, this, and this, for example, it is 3 coins. Again, 0, 1 here. What is the minimum number of coins required to get a change for k? No, not sufficient, Prerna. Include count in dp expression. That's the right direction to think, but how does it come in? Wonderful. Perfect, guys. Perfect. Missing something, Tejasvi. +1. Exactly. So when you take it, instead of just adding value, you will add 1 there. There should be minimum of, sorry, I missed that. Minimum of this or this. If you take it, you will add 1 to the answer because you're taking that coin. If you don't take it, whatever is in the previous answer, dp of I minus 1j, you will use that. Last rapid fire question. This is question 3, by the way. You need to check if it is possible to divide coins into 2 groups of equal value. Means, for example, if I have the coins 3, 10, 5, 6, 2, I can put it as 3, 10 and 5, 3, 2 maybe. Right? Or 5, 2, 8, 13. Yeah, 5, 6, 2. Then it is possible. So group 1 has the same sum as group 2. There are many possible combinations, but it is possible that at least one such combination exists. What do we do for this? Sort, nothing to do with sort. If you sort here, so it will come something like 2, 3, 5, 6, 10. So that's not really going to help you. Tejasvi's answer is right, actually, guys. See, let's add all of this and let's say it will come out to be some variable called total. If it is possible to get a change for total, means if it is possible to check if there is a sum of coins which will equal to total by 2, then sum of all the remaining coins is total by 2. Here total is 26, right? If you know that a group of coins here can give you a sum of 13, then the other group sum is obviously 13. That is right, unless the total itself is an odd value. In that case, it is not possible. Then this will fall into the first problem that I gave you in rapid fire. So this is basically directly linked to first problem, but k equal to sum of array by 2. Exactly, we have to check for total by 2 in the answer. Okay, make a quick note of this. And when you're writing it down, try not to look at the DB expressions that I have here. Try to write them on your own if possible. But at the same time, don't note it wrong. Verify after you write at least. Last 1 minute. Last 30 seconds. Shall we move ahead? Do you need more time? Moving ahead then. Okay. Moving on to the next question, everyone. You're given a matrix of size n cross m. Given a matrix of size n cross m with a few blocked cells. So the cells marked with X are blocked here. From any cell, you can travel in two directions. You can either go right or you can go down. From any given cell, you can travel in only two directions. Either you can go right or you can go down. You need to count the number of ways to reach bottom right cell from the top left cell. Bottom right is nothing but n minus 1, m minus 1. Top left is nothing but 0, 0. I can go like this. This is one way. Or I can go down and go like this. Or I can go here and go like this. There are many ways like that, as you can see. You need to count how many such ways are there. If you think you figured out the answer, you can share the DP expression in the chat directly. So you remember how we deal with these problems, right? You imagine that you are at some I comma j. Here it is not an array, right? So you can't do that dot 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 and point it. It's a matrix now. So we should imagine that we are at some position I comma j, at some cell I comma j. Now, what are our options? You can come to I comma j from above or from left. There is only one way to come from I comma j from above. And there is only one way to come from I comma j from left. So if you know there are x ways to reach here and y ways to reach here, the answer for I comma j is going to be x plus y. Perfect. Exactly. Perfect. So that is it. That is how our, what do you say, DP expression will look like. DP of ij is equal to number of ways to reach. Basically, our DP state here is something like this, right? Number of ways to reach cell I comma j. So DP of ij minus 1 is the cell on the left. DP of I minus 1j is the cell above it. If you know the number of ways to reach them, then you have your answer. If it is blocked, obviously the answer will be 0 there, because you cannot reach that cell. But that is not the tricky part of this problem. The tricky part of this problem is actually the base conditions. Okay, let's say that there is one way to come here, because that's where you're starting. Obviously, there is one way to reach all the cells in that column. But if you do the same for this side, which is row, one way to reach here, one way to reach here, one way to reach here. But once you encounter a block cell, it will be 0, 0, 0, 0 from here, right? There is no way that you can go to those cells if you have a block cell in your way. Similarly, if I had a block cell here, then all these would have been 0, 0, 0 instead of 1, 1, 1. Means for your base condition, you need to keep filling once until you encounter a blocked cell. And everything after that blocked cell will be zero. And that's one way to write it. But again, you can simplify your base condition. You don't have to, write it explicitly. You can simplify it by saying that, okay, instead of handling all that, explicit separately, I will add a row of zeros and exactly extra row and column of zeros. Perfect. N+1 size matrix. This idea is similar to what we did in knapsack, right? We had an extra row there to simplify, accessing the base condition. That's what we are doing here as well. But we should put 1 here. Without this 1, it will not work. You should put a 1 here. So if you add that extra row and column of zeros, then your base condition is extremely simplified. Then your base condition will be simply dp of 1, 1. You should make it 1 and then you start your logic. Not 0, 0 because now 0, 0 is the extra 0 that you have added. Make a quick note of it. Where is the answer? Answer will be a dp of n, m because we are adding 1 extra row and column. Table size n+1. Can you repeat the first approach of filling zeros? Firstly, there is only one approach here. Acha, you're talking about, okay, got it. Filling it like this, right? Okay. So here, when you want to fill it without that extra row of zeros and ones, you keep putting 1 until you come across a blocked cell. After that, everything is 0, 0, 0, 0 from there. Same in this direction. 1, 1, then you have a blocked cell, so 0, 0, 0, everything below it will be 0. So there are 1 or 2 different variations of this, which we will discuss after we take a short break. We'll meet again at 22. And please mark your activity before you go for a break, guys. Don't forget to mark your activity. I did not enable it yet. Just give me a second. I will enable it. Mark activity has been enabled and I gave you 2 extra minutes for the break. Don't forget to mark your activity. Mark activity has been enabled and I gave you 2 extra minutes for the break. Don't forget to mark your activity. Mark activity has been enabled and I gave you 2 extra minutes for the break.
Recording stopped.
Let me start the breakout rooms now.
Recording in progress.
All right, everyone, it's time to resume. Videos on, face visible. Videos on and face visible. Faster, faster, guys. Let's begin. Faster, videos on, face visible. All right, so for the next question, which is a follow-up on the previous question, let's say that you are given an n cross m matrix with no blocked cells. Then what will be the answer? Everything else from the previous question will remain the same. You can travel in only two directions. You can either go right or go down. You need to start from 0, 0 and reach n minus 1, m minus 1. How many such ways are there? You need to count that. So all the other things from the previous question will remain as it is, except there will be no blocked cells at all. Obviously, we can still use the previous DP expression that is there. But now when you're assured that there are not going to be any blocked results, I hope now you can imagine that there is going to be some kind of a formula or something, right? In relation to n cross m that you're given. So now I would like you to identify what that formula or what that calculation is, to get the count of how many ways are there to reach n minus 1, m minus 1 from 0, 0. From top right to bottom left, how many ways are there? That is not the right answer, Divya. That is not the right answer, Nikita. No, Anish. That is not the right answer. N plus m factorial by n factorial and m factorial. Close, but not right. Okay, listen to this story. Maybe you'll get the idea. So let's say there are 10 friends. Let's say there are 10 friends. And you have six what do you say, type 1 chocolates and 4 type 2 chocolates. You have 10 friends and you have 6 type 1 chocolates and 4 type 2 chocolates. How many ways are there in which you can give these chocolates to your friends? How many ways are there in which you can distribute these chocolates to your friends such that every friend gets exactly 1 chocolate? Ten factorial by 4 factorial into 6 factorial. Can you put it a bit more in terms of C combinatoric syntax? 10Z6 plus 10Z4. Okay. Any other answers? Any other answers? Two into 10Z6 into 10Z4. Okay. No. Tejasvi's answer is correct, guys. It is 10Z6 or 10Z4 because 10Z6 is equal to 10Z4. See, if you have 10 friends, if you know how many ways are there to give 6 chocolates to 10 friends, then all the other friends are getting 4 chocolates, right? Remaining 4 chocolates. They are not different ways again. So the number of ways to give 6 chocolates to 10 friends is 10Z6. Thank you. You know that. It is 10Z6. Exactly. And each of those ways, each of those 10Z6 ways, the remaining 4 friends who didn't get a chocolate are getting the type 2 chocolate. So 10Z6 is the answer. But we know 10Z6 is equal to 10Z4. Means if you reverse the calculation, if you say that I want to give 4 chocolates to say 4 friends, type 2 chocolates to 4 friends, then all the other friends who did not get a type 2 chocolate, again they are getting type 1 chocolate, which is nothing but 10Z4, which is exactly the same thing again. So 10Z6 or 10Z4 is the answer. because 10 c6 is equal to 10 c4. Fine, all that is good. If friends are toxic, then depends on their strength who can take how many. Yeah, that's right. Or you can, put each of them in one room and say that I'm not giving others a chocolate, but I'm giving you one. That's one way to be, a bit more psychotic. Anyway, so how is this friends problem related to our matrix problem? See, guys, now if you look at any way which will take us from the top left of the matrix to bottom right of the matrix. So for any matrix of size n cross n, you will go right m minus 1 times. You will go right n minus 1 times. So m minus 1 ways are there to go right. N minus 1 steps have to be taken to go right. And n minus 1 steps, instead of times, we'll call it as steps. You have to make n minus 1 steps to go down for sure. In which combination you do them, that doesn't matter. I can choose to go down and then go right here. And then I can choose to go down and then right. And then I can choose to go down from there. But the number of times you go down will still remain same. And the number of times you go right will still remain same. So in whichever way you go from top left to bottom right, the number of times you go right will always be same, and the number of times you go down will also always be same. And that is n minus 1 times to the right, to go down, and n minus 1 times to go right, giving us a total of n plus n minus 2 steps to be taken. Out of n plus n minus 2 steps that you have, you need to, okay. Based on this, tell me what is the answer. Now link the friends problem, link this, and tell me what is the final answer. Wonderful. That's right. Perfect, guys. That's right. So the answer is number of ways to select n minus 1 steps from a total of n plus m minus 2. Exactly, which is exactly equal to m plus n minus 2 c m minus 1. Last 30 seconds. Please make sure you have your video on, guys. Even if you turn it off, please turn it on after a few minutes. All right, moving on to the next question. Okay, for the next question, you are given a 5-dimensional matrix with a list of blocked cells. You are given a 5-dimensional matrix with a list of blocked cells. From any cell, you can go to the next cell by incrementing any one of the dimensions by 1. By incrementing any one of the dimensions by 1. You need to calculate the number of ways to reach P, Q, R, S, T from 0, 0, 0, 0, 0 in a matrix of size P, of size P, Q, R, S, T. In a matrix of size P, Q, R, S, T. So what this question is saying is basically, if you are at any I, J, K, L, M, for example, from I, J, K, L, M, you can either go to I plus 1 J, K, L, M, or you can go to I, J plus 1 K, L, M, or you can go to I, J, K plus 1 L, M, then L plus 1, then M plus 1, like that. You can increment any one of the dimensions by 1, and you can go there. This is where our imagination starts to melt. 1D array, okay, you can imagine. 2D array, you can imagine. 3D, okay, you can try. It's a bit tricky, but you can imagine. Once I say now it's a 5-dimensional matrix, it's not about imagining a 5D matrix anymore. You can't do that. So you need to look at this problem, a bit more abstractly. You need to abstract away all the complicated parts. So whatever is your observation, please feel free to share now. I am kind of confident that many of you figured out what it is. Whatever observations you made, you can share. If you have a DP expression, you can share that. All of these increments can happen in any sequence. It's not about they will happen. It's about you can do it. You can go from IJKLM to any of these cells, as long as they are not blocked, as long as they are not in the list of blocked cells that you are given. A 2D DP array of PQ and ST, P into Q into R, and S into T. You don't exactly need a 2D array. You can just go ahead with a 5-dimensional array here for your solution. So one thing that I hope you have observed is it is somehow related to the previous problem. That's right. Whatever Tejasvi shared is correct. Whatever Asghar shared is correct. It is directly related to the previous problem. In the previous problem, from I comma j, you are allowed to go right, which is ij plus 1. And you're allowed to go down, which is I plus 1j. That's right, Padman. Means in the 2-dimensional variation of this problem, you can increment I, which will make it I plus 1, or you can increment j, which will make it j plus 1. This is exact same problem in 5 dimensions. That's it. Absolutely no other changes has been made. Instead of saying going right and going down, I said you can increment any one of the dimensions. That's it. I just changed the wording to keep it more consistent. Going right is incrementing the column. Going down is incrementing the row. In our previous discussion. it means that this is going to have the dp expression something like dp of I, j, k, l, m is equal to I minus 1 j, k, l, m plus I, j minus 1 k, l, m and so on. I, j, k minus 1 I, j, k, l minus 1 and lastly I, j, k, l, m minus 1. Focus, Chandan. You lost track. Okay, so this everything else will, you can handle it, guys. The base condition, you can handle it on your own. Blocked or not, you can check. Depends on how the input is given for the list of blocked cells. You know where to find the answer. Yeah, which is pretty much it. So the summary is basically you just have to, abstract everything. You don't have to imagine every single thing. If you are able to abstract it by saying that, okay, how many ways are there to reach IJKLM? I can come from I-1, I can come from J-1, I can come from K-1. And if I know all the ways, I can just add them up. So instead of visualizing the matrix on which you are going to traverse, you just visualize the abstracted variation of the problem, which is where you are and how you will get the answer. All right, let's move on to the next question. This is like a waste, A waste from I-1 and B waste from J-1 and so on, and then A, B, C, D. Exactly. That is right. Exactly like that. If you are interested, this is a very fun problem to write code for. And I don't think you'll get a lot of opportunities in your life to declare a 5-dimensional matrix. So, and use that 5-dimensional matrix. So just it is a good, fun code to write. So definitely try it out. 20 seconds. All right. So formula will be P plus Q plus R plus S plus T minus 5 C P minus 1. Yes, that is right. No, that is not right. No, that is not right. That is not enough. That is insufficient. In no blocked cell scenario, still that is insufficient, because in our two-dimensional matrix, you have either this or that. But in a five-dimensional matrix, if it is not this, then there are 4 other possibilities. So you can't say directly P minus 1 there. Moving on to the next question, which is a very fun question. My second favorite question in DP. Or third favorite. One of my favorite questions in DP. So here, you are given a matrix of size n cross m, and you are given Q number of queries, each query containing 4 integers. For example, the first integer is 1, 2, 4, 3. Let's call them I, J, K, L. And maybe next is 0, 0, 2, 4, something like this, 0, 1, 3, 3, etc. Let's call them I, J, K, L. And the question here is basically, you need to print the sum of all the elements in the submatrix Ij to Kl, where Ij is basically the top left of the submatrix and Kl is bottom right of the submatrix. To identify any unique subarray, you need start index and end index, right? Similarly, to identify any unique submatrix, all you need is top left and bottom right. So that is what you are given in the input, top left and bottom right of different matrices. And you need to calculate what is the sum of the elements in that submatrix. 1, 2 and 4, 3. 4, 3. So this is nothing but this submatrix. One, 2 and 4, 3 is this submatrix. Similarly, 0, 0 and 0, 1, 2, 0, 1, 2, 3, 4. This is 0, 0, 2, 2, 4. And so on. Please don't share the solutions until I ask you to share. Write down the solutions, time and space. There are multiple ways in which we can approach it. Please write down the question completely, properly, carefully, and figure out different solutions. Do not share the solutions until I ask you to share. Come with different solutions for this. Solutions, guys. Time and space only. Your solutions should definitely have Q, guys. You cannot have a complexity without Q. There are Q number of queries. That's right. Q and M, comma 1 is a simple brute force way of doing it. Perfect. QNM1, QNM1. Come on, guys. You can do better than that. Any other solutions? Raju, do you want to correct your second solution complexity? NM plus Q comma NM. Great, great. That's a great start. Q into 2 bar N. You don't really need a 2 bar N solution here. That won't be 2 bar N, by the way. I'll tell you what it is when I come to that. Basically calculating every submatrix, right? Because initial works just gives really. Yeah, it's not about it doesn't work, it works or not. It's more about how you're doing it that I'm concerned about. A 2 bar N solution is not really required. Yeah, 2 bar N solution is not really required. You will not have a situation where you have to select multiple elements which are not in a sequence at any point of time. And M plus Qn comma NM, great, great. Okay, nice. Great, we can do that. So let us discuss the solutions, guys. Solution 2 and 3 now. Solution 2 is basically optimizing on solution 1. Solution 1, you just have to traverse the entire submatrix for each query, which is Q and M. Now for solution 2, instead of traversing the entire submatrix, if you could compute and store the row-wise prefix sum. If you could compute and store the row-wise prefix sum, then you don't have to traverse that entire row to get the sum, right? If you remember back to our subarray sum problems. Remember? Prefix sum, first problem, subarray calculation, yes. Okay. Yes, last sum minus first sum minus one index. You'll get the total. All right, great. So you take a prefix sum, prefix sum, prefix sum, prefix sum. And as we know with prefix sum, you don't really have to store it in a new array or new matrix entirely. You can just update it in place. So we'll go with the method where we are updating it in place directly. Then when they ask you to calculate the sum of this matrix, for example, then all you have to do is just go this row, this row, this row, this row, and so on. You don't have to traverse the columns of that row. To get the prefix sum of every row, it will take nm time. Because we update it in place. And to answer every query, it will take how much time? Into? Exactly. Qn, perfect. Q into n, perfect. With constant space. Because we are updating in the same matrix. So you take prefix sum of every row. Prefix sum, prefix sum, prefix sum, prefix sum, prefix sum, like this. You update it in the same matrix. Now for the next solution, once we take prefix sum, we will prefix sum on the rows. We will also take prefix sum on the columns. So once you take row-wise prefix sum on that matrix, we will also take column-wise prefix sum. On that matrix, we will also take column-wise prefix sum. For solution 3. Now, what is happening here is, let me take this cell for example. What is containing in this cell? The prefix sum of this row till here. That's right. The prefix sum of this row till here. And the prefix sum of this row till here, which you have merged into this. Exactly. It is basically containing the sum of all the elements in the submatrix 0, 0, 2. That's it. Now, once you understand this, now let's say that you are given some I, j here. And some k, l here. Now you want to know what is the sum of this submatrix. Can you tell me how will you calculate the answer? Okay, first, that's right. Matrix of k, l first. Matrix of k, l will give you the matrix, this entire submatrix, right? Elements in this entire submatrix, exactly 0, 0 to kl. But we don't need all these and all these, right? We only need these. So first, let's remove these. How will you remove these? No, no. There is no simpler way to color it. Yeah. See, it should be one column before J, right? It should not be in the same column as J. Then you're missing row elements in that column. It should be one column before J. And yeah, same column, same row as K. So this is basically K comma J minus 1. Exactly. So now you subtract matrix of K comma J minus 1. Now let's get rid of this. Let's get rid of this. What is this index? Perfect, you got it. One row above I, but the same column as L. Same column as L. Exactly. Minus matrix of I minus 1 comma L. But as you can see, this green zone is being removed twice, right? Once by yellow and once by blue. So we need to add it back once. What is this cell of this that we need to add back to the sum because it was removed twice? It's not I comma j. I comma j is including this and this and this. I minus 1, j minus 1. That is right. That is cell above ij, right? Not ij itself. Diagonally above ig, which is I minus 1, j minus 1. Because it was removed twice, we need to add it back once. Because it was removed twice, we need to add it back once. So there are some things here which I hope you will handle it on your own. For example, you will do this only if, j greater than or equal to 0. Sorry, j greater than 0. You will do this only if I greater than 0. You will do this only if I greater than 0 and j greater than 0. Time and space. Perfect, perfect. nm plus q, comma 1. Row wise prefix, column wise prefix. And this is to answer queries. Last 30 seconds. Then we'll see how this can be reframed as a DP solution. So basically, if you want to reframe it as a DP solution, then we just want our matrix I comma j, DP of I comma j, to contain the sum of the submatrix 0, 0 to ij, right? Every dB of ij should basically contain the sum of the submatrix 0, 0 to ij. Then you can do this to get your answer. But to get this, now you need a dB expression. Now for our dB expression, let me draw another matrix. Yeah, got it. Let me draw another matrix here. Now for this, now let's say I want to get the answer for this I comma j. Where will I get the answer for I comma j from? If I try to access I minus 1j, it will give me sum of this submatrix, right? dB of I minus 1j is giving me the blue highlighted area. Well, that is great, but it is not giving me this entire column. For that entire column, I can access just a second, guys. This is not dB of I minus 1j. This is dB of I minus 1j. That's right, Vashit. This is I minus 1j. This is ij minus 1. I mean, you don't have to erase it. I'm just erasing to match the colors, basically. You will basically add them. Plus I minus 1j. But as you can see, this region is being added twice. So we need to remove it once. Exactly. So this we need to remove it once by subtracting I minus 1, j minus 1. That is right. But that is not enough. We need to do one more thing, which is plus. Exactly. Perfect. Perfect. Plus, we need to add the element at index I comma j. Matrix of ij. It will not be dp of ij unless you're updating your dp in the same matrix. It will be matrix of ij in that case. So this dB expression is basically doing what our prefix sum plus, row wise prefix sum plus column wise prefix sum is doing. A combination of it, whatever it is doing, this is it. being done directly by the DP expression. Once that is done, you can use the above calculation again to answer. Instead of matrix, you will do DP there. That's it. Make a quick note of it, last 30 seconds. Then we'll move on to a very fun problem. Moving ahead to the next problem now. And this is again one of my favorite problems. How can we guess whether any given problem can be solved by DP? You should obviously observe for DP properties first. So the problem that I showed you just before, it doesn't exactly, it is not necessarily solved as a DP problem. As I showed you, first I showed you how to do it like a prefix sum problem directly. But I showed you how to reframe it as a DP problem, which is the same thing which we did with Kadani Salitam, if you remember in our last session. So these kind of problems are not exactly DP problems. They are just, reframed as DP problems. So you cannot use your traditional, methods of how to approach a DP problem. You imagine at IJ state and what you are doing. Is there overlapping subproblems, optimal substructure? If you cannot do that, then most likely it is not a DP problem, or it can be solved without DP. But any other problem which you suspect can be solved with DP, you first analyze what if you're at any I, jth state, what are your options? Then from there you will check if you have any overlapping subproblems or any optimal substructure, which will tell you that okay, you can do DP here. Then you will go with the next steps. Do we get the optimal solution using DP? Very subjective question. Depends on problem to problem. Most of the problems, yes. But there will be a set of problems which DP will not exactly give you optimal solution. What is the time complexity for the previous problem in the DP scenario? In the previous problem for the DP scenario, all we have done is merged the row-wise prefix and column-wise prefix into one calculation. So it will become nm plus q instead of nm plus nm plus q. And it will be constant space if you're updating in the same matrix instead of a separate DP matrix. Which is more important, space optimization or time optimization? Most of the solutions will give preference to time optimization. If two solutions have a same time complexity, then you'll try to optimize space. That is right, Asghar. Most of the time, space optimization is just a bonus. Or it may also depend on the type of question, if it is particularly tailored for you to use optimized space. Depends on that as well. Okay, moving on to the next question, everyone, which is a very nice question. It's a very fun question. You need to calculate the maximum submatrix sum. Calculate the maximum submatrix sum. Basically, this is like the maximum subarray sum problem. Instead of subarray, it is submatrix. That's it. Any submatrix here could be a maximum, could have a maximum sum. Visually, it looks like this submatrix has the maximum sum. Or maybe even this. Yeah, visually this looks like the maximum submatrix sum here. But of course, there could be a better submatrix, but just letting you know how you should look at it. So write down solutions, time and space. In fact, you can share the solutions directly if you have any ideas. You can share solutions, guys. Any solution that you have. 2 and m, 1. Did you mean m square? I can assure you that there is no 2nm, 1 solution. Or 3nm, 1 solution. There is no 3nm, 1 solution either. N into m square or nm whole square, Vashit? Nm whole squared. Yeah, there is one solution with nm squared, which is a very nice solution. n square into m square comma 1. Yes, we can do that. So here, guys, this is a brute force solution, obviously. Nm whole squared is a brute force solution for us. I mean, not exactly an m whole squared, but yeah. What is the brute force solution here? In words. In words, the brute force solution is check every submatrix sum and update maximum. That's a great idea, Rutvik. We will come to that as well. In simple words, the brute force is basically every submatrix you calculate the sum and update the maximum. For that, we should know how many submatrices are there in any matrix, right? And we know that to calculate any submatrix, it is enough if you have a top left and a bottom right. So if you look at this matrix, I can have a top left anywhere. Here, 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 here. Any cell could be a top left for me. Let's say I'm talking about this as the top left matrix. Then my bottom right could be any of these cells. Any of these cells will be my bottom right of this matrix. Means we can say that there are big of nm possible top lefts. And there are big of nm possible bottom rights for each top left. It means that there are big of nm whole square. I'll just write it like this. Number of possible submatrices. And if you want to calculate the brute force way to calculate the sum of each submatrix, it will take into nm time. And if in this complexity, if you take n equal to m, or m equal to n, basically, then this is something like big of n power 6, right? Which is a very fun code to write again. Did you ever write 6 nested loops? No? You can try it out. Okay. That's a simple brute force way. But you can get the sum of the submatrix in big of one time if you apply the previous solution. Any submatrix sum, you can get it in big of one time, right? From the previous solution, optimized solution from the previous problem. So it will take nm time to calculate your dp or prefix, row-wise prefix plus column-wise prefix. Then for each of the nm square submatrices, you can get their sum in big of one time. You can get their sum in big of one time. Which is a nice solution, but if m equal to n case, it is still big of n power 4, which is not very nice. So clearly here we can do better than that. Here we can do better than that. And here, to understand solution 3, we need to look at this problem differently. Second solution once again. Second solution is basically calculating the, what do you say, from previous problem. Solution 3. Then every submatrix sum, you can get it from the previous problem, solution 3. Which is prefix sum row wise and column wise. Then can use that answer calculation to get the submatrix sum. Now let's understand solution 3 over here. To understand solution 3, I hope you all remember how to do Kadhane's algorithm from our previous session. Kadhane's algorithm, maximum sub-array sum, n, one solution, prefix sum, but don't carry forward negative prefix sum. Yes. Okay, so we are going to use that, but in a different way. All right, let's try using that now. So for my solution 3, I am going to mark start column and end column. I is going to represent my start column. J is going to represent my end column. So at any point of time, we will only consider the elements in this range, start column to end column range. Originally, it is just one column, so we can just add all those columns directly. Two, 13, minus 5, 8, 2. I simply took the elements from this column and I added it to an array. And I added to an array. Once I add it to my array, I will simply do. I'll do what? Prefix sum, Kadhane's algorithm, exactly. I'll do Kadhane's algorithm on this. Yeah, which is prefix sum without carrying forward negative prefix sum. That's it. 2, 15, 10, 18, 20. So till now, my answer is 20. This is the maximum I could find till now. Now, once I finish with the first column, now I will move my J to the next column. I is start column, J is end column, right? Now I have moved J to the next column. Now what am I doing again? I will add these to the array. Exactly, we will add it to the array. This will become 2 plus 3. This will become 13 plus minus 20, minus 18, 14, and 5. Once I do this, obviously now this is gone. These will be in our array. Let's do Kadhane on this again. 5 minus 2, don't carry forward minus 2, minus 18, don't carry forward minus 18, 14 and 19. If it were a regular prefix sum, you would have taken everything along. Because it's Kadhane, we are not. In order to get the maximum sub-array sum. In order to get the maximum sub-array sum, we should do Kadhane on this. Obviously, Maximum here is 19, but we already found 20, which is bigger. Answer will not update. And let's move our j to the next column. And by this point, with this column, you should probably understand how it is working. -5, you will add it to this. Let's take blue color. 0, 1, -19, 18, and 17. Max of all column, we will check each time using Kadani. That's right. So basically, if you observe here, now let me just update my array after I added everything. And let me do Kadani on this 0, 1, -18, 0. Okay, -18, you won't carry it forward. So this will be 18 and this will be 35. See, the max here that you're getting is 35, right? The maximum you got here is 35. You need to pay attention to this part of the solution, especially. Yeah, according to Kadani's algorithm, here the maximum is 35. How did you get 35 here? That 35 came when you added elements from this row to this row. 18 and 17 basically. And that 35 came because of elements from this column to this column. Means basically 35 is the sum of these elements. Following? So we are basically compressing all the columns into one array on which we are doing Kadani. So once you keep doing this for all the columns, you're basically covering all the submatrices. In the next iteration, J will go here. In the next iteration, J will go here. In the next iteration, what will happen? In the next iteration, what will happen after J reaches the end? Exactly. I will go to next index and J will again start from here. I will go to next index, J will start from here, and your array will reset with these elements once again. And you will continue your logic. Here, here, here. How to identify the submatrix? So in your Kadane, whatever is the maximum that you're getting, you just have to observe from where did you get that prefix sum. So that is the prefix sum after -18, right? So after -18, whatever elements you added gave you 35. Means starting from this row till this row, it gave you 35. And when you are doing this process, where were your I and J? That will be your columns. So you know start and end row, you know start and end column. Then you have your submatrix. We need to keep track of start and end indices to find submatrix, right? Yes, that is correct. So along with the answer update, if you can keep track of the start and end row, as well as update your start and end column when you update your answer, then you can maintain the answer submatrix indices. So this idea is basically a 2D Kadani algorithm. A 2D Kadani algorithm. And I want you to help me write code for this. I want you to help me write code for this. So first tell me, what all variables do I have to initialize apart from answer? Nothing else. Yeah, nothing else over here. Yes, array will come, not right now. It will come later. The first step of our logic, we need to write code for ing, right? Top index and bottom index. No, start column index and end column index, right? Not top index and bottom index. ing is what we have to loop on. That's right. I will go from I equal to 0 to I less than m or n. M, right? Number of columns. ing are for columns, right? M is the number of columns. Now for each I, every time you move I, your j goes to the end and it will reset from I again, right? Whenever I moves, j goes to the end and it will come back to the I, and then it will go from there. So inside the loop, we need to exactly create an array. We'll come to j loop. Whatever you said about j, that is correct. But first we need to create the array for array of size. Perfect. Array of size and initialize everything to 0. Array of size and initialize everything to 0. And inside here, we will do j equal to 0 to, sorry, j equal to I to j less than m. So I is basically the start column and j is our end column. No, Tejasvi, ing are looping on the same columns, right? I is start column and j is end column. Okay, now inside here, now you need to add your jth column elements to the array, right? Index by index. While you are updating index, you will also update the sum. Definitely, Bhargav. I'll give you more time after the code is done. So we need to update it index by index. While updating index by index, you can also do Kadana at the same time, right? Anywhere you are going there, anywhere you are traversing, you can do Kadana along with it. For Kadana, we need two important variables, right? In the same array, exactly. In Kadana, we need two variables, exactly, prefix and the maximum prefix sum, which is, oh, you can say answer, but we already have answer as a different variable. Or we can use that variable itself. Maybe that should help us. Prefix sum equal to 0. For int, not int, for basically k equal to I to k, sorry, k equal to where, guys? K equal to 0 to exactly k less than n. K equal to 0 to k less than n. First, you will update your array. Tell me, what should I write here? Array of dash equal to dash or dash plus equal to dash. What should I write here? Array of I want to update my array here. No. Prefix sum is different. You will not add it with prefix sum directly here. Array of k plus equal to mat of I comma j. Perfect, Vashit. Good job. Array of k plus equal to matrix of not I comma j, matrix of k comma j. That is right. Kth row, right? Kth row will go to kth index in array. And then you will do prefix plus equal to array of k. And then you'll update your answer. Exactly. Answer, comma, prefix sum. And lastly, you will update prefix equal to, that's right, max of prefix sum, comma, 0. Which is a signature step in our Kadanes algorithm. Can you tell me what is the time and space here? What is the time and space here? Perfect. Perfect, guys. Perfect. This is solution number 3, which is m into n. M square into n, comma, n. Perfect. N space for our array. Yeah, if m equal to n, it is n cube. That is right. If m equal to n, then it will be big of n cube. Please make a detailed note of it and please try writing the code without looking at my screen as much as you can. At the same time, don't write down a wrong code. Faster, guys. I'll give you 1 more minute. Before we move on to next discussion, please mark your activity. Don't worry, I'll give you more time. I'm giving you 1 more minute for you to write down. Please mark your activity meanwhile. Last 30 seconds. Moving. Okay. I'll wait a few more seconds. Meanwhile, if you have any doubts, please ask, guys. It's a very nice problem, very interesting problem. Is it fine if we move on to the next discussion? Yes, yes. Okay. All right. Let us move on to our next discussion. So for our next discussion, we have 2 more DB problems. And they are very interesting problems. So I cannot tell you right now, it's not the right time to introduce interesting problems. I'm sure you're already exhausted to a certain extent with the problems we already discussed. But one thing that I want you to remember, guys, this is, fundamental concept of DP. I told you several times how to start a DP program, right? Imagine that you have a lot of positions and you are at some ith position. What can you do from there? 90% of the problems you can solve it like that. You figure out that part, what will you do at that position? Then 90% of the problems you'll be able to solve directly of the DP problems. Just that one step, if you master that, it will be very, very simple and very nice. And try to inculcate that thought process in your assignment problems as well when you're doing your assignments. The next point is tomorrow's 2 DB problems that I'm going to discuss are a bit tricky. You will not understand them until you solve at least 1 or 2 of the problems that we discussed today on your own. After my session is concluded today, please don't go back to your old self. Okay, I am done with smart interviews. Now I'll focus on my other things of the life. Whatever other things you have going on in your life. They may or may not be important. I'm not saying that they're not important. I'm saying that this should be important. And you need to prioritize it. And before my tomorrow's session, please try to solve at least 2-3 problems from today's discussion. Every single problem is there in our Smart Interviews Primary. Page number 17, 18. If you visit those pages, 17, 18, maybe 19 as well, you will find all the problems, every single problem we discussed today, you will find it there. Please, not please. I want you to promise me that you are going to do it by saying, yes, I will get it done. Don't worry. At least 2, 3 problems. I want your yes in the chat now. And please stick to your word. Okay. Tomorrow's session, try my best. That's great. That's great. And I'm only asking you to focus on what I discussed already. Other things, then it's okay, you'll try in your own time. I'm not talking about that. Whatever we discussed, the entire solution, the breakdown, the time and space complexity, we discussed, almost every single detail. Those problems you try to code. That is what I'm asking you to do. So you just have to study and apply. Every single thing is there in your notes. And last thing, guys, this is the last thing. Maybe I'll discuss it tomorrow. Yeah, I'll discuss it tomorrow, guys. Don't worry. Cool. That's it. I'll start the breakout rooms now. And see you again tomorrow. Can we have a lab tomorrow? We will plan something like a lab.
Recording stopped.
Yeah, we will plan something like a lab. Maybe what you can do is in a regular lab timing, you just post queries and we will address your queries within 2-3 minutes. We will be online continuously from something like 9 a.m. to 11 a.m. And any query you post, we will try to address it within 1 or 2 minutes. So that is something that we can do. We cannot have a dedicated lab as such, but we can be available online to address your queries instantly. So you can practice in the duration at your own house, in your own time, in your own way. Whenever you have a query you post in 9 to 11 duration, we will address it within 1 or 2 minutes. That is something that I can do. Are you in for that? Okay, we'll do that. All right, guys. So 9 a.m. to 11 a.m. tomorrow, we will do this exercise and see how it goes. And I have started the breakout rooms now.